Okay, I think we can start. Today's lecture, as I wrote up here, is about the discovery of the Higgs particle, about one of the biggest conjectures in particle physics, which is called supersymmetry. And if I have time, something about what people are talking about doing or building in the future, meaning particle accelerators. Interestingly, I just came back this morning from 2 days at CERN. This lecture is essentially about CERN, which is where the frontier is in particle physics. So I'm well prepared for the lecture, I guess. So anyway, let's look at what we're going to do. First, we're roughly halfway through the course. We're now at the 7th week in December, and the topic is what I said. So what we've done is pretty much cover this telescope picture of the standard model with a few things now that are maybe the most interesting, and we're looking at in a little bit more detail. Today we'll focus on the Higgs particle itself, and what it took to discover the Higgs particle and what the evidence is for the Higgs particle itself, and at least as importantly, what the features are that are special about this particle, what makes it special, and what we don't know that people are going to have to try to figure out in the future, which is part of the future. Second top, so I'll do that the first hour. The second hour, I'm going to talk about a subject called supersymmetry. And that basically is a conjecture that this picture of these quarks and leptons that we have is actually mirrored by a whole set of them that we have never seen yet, called supersymmetry. The reason for it has to do with one added symmetry that might exist in nature. But the reason it's attractive is kind of first the generic reason that nature tends to be symmetrical. So we have almost everywhere in nature that everything is symmetrical, and then there are differences that we find that are there. This whole picture that I've shown you so far is not symmetrical, because you could have a whole mirrored set that had what we call bosons instead of fermions, having the complete set. I'll talk about that in the second hour. It would solve a huge number of really important problems in physics, but we haven't seen it. So it's a big puzzle. It's a puzzle for the future, and it also illustrates kind of sometimes maybe the most attractive path, and explanations we have don't work out. So this may not work out, or maybe we just haven't seen it yet, and I'll show you. So this is something that I'd say is in progress. Just like in a few weeks, I'll talk about the problem of dark matter, which is a similar one where we have a lot of reasons to point for what dark matter might be, and yet we haven't been able to find it. Might be that we're going down a dead end and don't see nature properly, or not. This is a big one. So this is really one of those kind of at the forefront problems that I want to talk about. And I'll talk just very briefly, if I have any time at the end, about the proposals like at CERN to build yet a future collider that would be bigger than one that we presently have. So when you see it in the newspaper or something, you'll see what they're talking about. Whether it'll happen or not is, again, a question of practicality, money, and whether the science case is strong enough. That'll pretty much finish the fundamentals of what we call particle physics. However, there's a piece of it that I haven't touched yet, and on purpose. That is the line here that's called neutrinos, because it is a subject that is much broader. And so after the lecture today, I'll start on a set of lectures on neutrinos. The reason they're so important, first, they're fascinating. It's the most fascinating particle of all, except for maybe the Higgs. And it has a lot of implications and a lot of history in particle physics, so it's the last subject in particle physics. but it also is one of the most prevalent particles in the universe. It has a lot of implications for astrophysics and even for cosmology. So this makes, for me, a good transition from the fundamentals of particle physics to the other subjects, which will be astrophysics, gravitational waves, cosmology. So the next few lectures, when we meet next time and in January, will be on neutrinos. And then we'll move on to gravitational waves after that. Okay, so let's talk about the Higgs. I talked about it at the end of last time. I can't in any way give you a kind of the right level explanation other than hand waving of this phenomenon. It's just it relies on very difficult concepts in particle theory, which were developed and came about after the fundamental models, which are the basis of the standard model, were developed for particle theory. That is based on what we call quantum field theory. And within quantum field theory, after you develop something like this whole standard model picture that I have been talking about, it was noticed that there are some symmetries. Again, I'm going to talk about symmetries and supersymmetry, but this is different. Some possible broken symmetries, and some features of the fields, features that I kind of showed in a cartoon, but features of the field that could be the explanation of how mass comes about, because everything I showed so far didn't give any hint why we have particles of mass. Even after this, we have this mechanism, we're still not, at the present time, able to explain why particles have the mass they do, why particles have, some of them, very funny masses, like I talked about the top quark last time, and it's heavier by maybe a factor of 100 than you'd expect it to be. So we have a lot of puzzles yet. But this picture that came almost naturally out of the mathematics and the theory that we had in particle physics was seen by a set of theoretical physicists almost independently at the same time, which often happens, in 1964. I've just shown here several of the titles of the crucial papers that came out in 1994. And they have the words that I said, broken symmetries. So we're going to talk a lot about symmetries, broken symmetries, implications of that, something about particular kind of mesons, having their masses, and something about these what we call fields, the fields being, in this case, space. And you'll see on the second and third papers the name Higgs. He's one of 6 people that did the first work, and then there was 2 more people that did really important work right after that I have in the lower right-hand corner. So they basically gave us the explanation for what made this seem very difficult. And so they were important also. And so there's something like 6 or maybe 8 people theoretical physicists that developed this idea. Higgs was unique in that he saw something the others didn't, and that is that if this idea of where mass comes from theoretically was true, it would imply that there'd actually be a particle in nature that had certain features that have to do with the mass, and that's the Higgs particle that we'll talk about today, and so it got named after him. But basically 6 people have been given the credit for developing this work, and it was almost a tie. If you look at the dates here, in the lower right-hand corner, you'll see it's October 1964. The other dates were July and August 1964. The whole credit, just because there's no other way to do it, not necessarily better papers, historically go to the ones who published first. Publishing first maybe a quirk, how long it took somebody to referee your paper or where you submitted it, but that's the best gauge that we have, so that was what was used. And these 3 people were the ones who were chosen to get the Nobel Prize for the Higgs once it was discovered. one of them had died by that time, Broad. So there was Englert and Higgs received the Nobel Prize for the concept of the Higgs boson to describe nature. So Broad is this guy, and Higgs is shown here when he was a little bit younger than now. And the others, as I say, played a very significant role. And it's another kind of picture of how a field develops, that you come to a point where a lot of people maybe have the same ideas or overlapping ideas at almost the same time. In this case, then, it took another 60 years to detect it, and it has special features, and I'm going to spend some time on that. I can't, as I said in this short lecture, give you any good explanation other than some fancy words you can walk away with on the bottom. This requires something we call spontaneous symmetry breaking. The person on the right is Nambu, and he had a certain picture of particle physics that had some particular kind of boson, and when Higgs and company came along, basically it got eaten up by this field as the words that people used, but it got heavier and acquired mass. So that's all blah blah as I said it, but I'm not able to show you mathematics. But the mathematics of it and the way the Higgs works is very well defined. How it came about theoretically is hard for me to explain, but once we define that we have a Higgs, it's very well defined what it does in terms of mass and what it is in terms of a boson, a particle itself. So you know what you're searching for. There's nothing in the theory that would tell us what the real particle that is the Higgs itself, what its mass will be. So the mass, again, we keep having that puzzle because I talked about other particles like the top quark where we had no idea and it was completely something else. In this case, we really can bound it some, but not a lot. I showed you actually results on the standard model that were used to basically bound it on the lower side. That you saw, we would have seen it when we did all the tests of the standard model on what I call the LEP accelerator, which I won't talk about today. If the mass were lower than about 100 or 110 GeV. So we know it's not lower than that. We also kind of know it can't be too heavy from a lot of other things that I haven't talked about yet. So we expect it to be kind of hundreds of GeV somehow, somewhere near 100 or 200 or 500 as we start doing the problem. Then as you think about if this has any reality, you have to be able to see it. What I show here is something you can calculate because you know how this all works. And I showed you a lot of diagrams last time. I'm going to show you a few more where you make the diagrams of how you produce it, and then you use Mr. Feynman's rules for how strong these different little vertices are, and you can actually calculate it. And that's what's done in the picture here. So here we start on the left-hand side with, if we have collisions between two gluons and they make a hadron, what would the cross-sections be to make various final states? The gluon to make hadrons is way up near the top, so it dominates. At lower level, you can hit the quarks and make, say, a W boson in a hadron. That's the line down here, and so forth. So basically, what happens is a theory comes along like this, and people do all these calculations to see what it should imply in the laboratory. Therefore, once you know what it should imply in the laboratory, then you can try to make an instrument that can see that. So this is just the cross-sections themselves. But then once it makes the Higgs is going to do something. It's going to decay in different ways, and those will get different energies. And if you look at the mass of the Higgs itself, which I left out of this picture, for different masses, it will make different final states. And that's just the different masses, how much phase space is available, and so forth and so on. So energies like there shouldn't be one below 100 GeV or so from the stuff I showed you last week. And once we start searching for it, if we're down here at energies like 100 GeV, it should be decays that are finally this B particle that we saw, a B and an anti-B particle. And that dominates. But if you go to higher energies, something else may be more significant. And all these happen. So if you really see it, you should be able to see it in these different modes. This kind of analysis that I'm showing you here is kind of done phenomenologically, calculating as best you can before you ever build the experiment or design the experiment. Ideally, that isn't the way it always happens. Sometimes you build an experiment and then you try to do it. But ideally, get what you're trying to do and then make that requirements to design and build an experiment. And for this particular case, that's pretty much what they did. So the highest production rate is gluon collisions to make the Higgs, and the easiest decays to see, just experimentally, are if they decay to the particle I showed you the discovery information for last time, that is 2 Z bosons, which I hope you remember are the particle that's responsible for the weak interaction if there's no exchange of charge, what we call the weak neutral current. That is the amount, the weak interaction charge is the same in the beginning as the end. And that's the Z particle, or just into ordinary photons, a pair of photons. Those are the easiest to see. Knowing that, then you go to the next step, which is to look and see how strong these are and what you can detect. And this is where I'm showing you, you do it by making the kind of diagrams that I showed you last time. So here we start with 2 gluons, and they're just symbolized by these kind of corkscrew lines. And then at any one of these vertices, you can actually calculate a strength. So 2 gluons make, as I did on the last slide, a top and a bottom. Those top and bottom, we only care about if the effective mass that they make is the mass of whatever the Higgs is. That's shown here. And then the Higgs has different decay modes, which is the right side of the graph that I showed you. And this is the second one. So you have these different diagrams, and you can calculate all these things if you know if you know the different strengths of the vertices that you're calculating, and that's how you get those curves that I showed here. So the first ones on the left were just the production. They're kind of what's done on this side. And then the second on the right side was what dominated in the decays. So once you do that, then the next problem is, say I look at this top one, a quark and an anti-quark making a pair of Z's and decaying. What are the backgrounds that also don't have anything to do with the Higgs, but make the same final state? And this is an example. So an example is we can smash 2 quarks together. We can make 2 of these neutral Z particles. It can decay into 4 leptons, and 4 leptons were one of the states we were looking for. So in the end, we have to be able to not only see what we produce, but how to distinguish these backgrounds, which are physics, not background, but they're backgrounds to this particular mode that we're looking for. And that's more or less the analysis that people do. So we have to be able to differentiate the signal from the background. And that can be done kinematically. They may have different distributions or different signatures that we can find to do one from the other. Or it has to be done statistically, which means they're both there, but there's an excess due to the new one that we're looking for. And that's what I'll show you in the end, is the signal for the Higgs. So in principle then, we basically just take all these diagrams, try to measure the ones that we have, and see if we can extract what we really care about, which is in this case, say, the bottom one here. The top is the one on the top of this, has the same final state. See, it's all little L pluses and L minuses. That's a lepton with a plus charge or minus charge. It's interesting, of course, but it has nothing to do with the Higgs. So we have to be able to distinguish those somehow in the distributions, and you'll see how that's done. Okay. So then you have to somehow build a device that's able to do this. And this involved first getting to the energies we're talking about, which is using particle beams. In order to get to the energies we care about here, you'll remember we finally saw that particle beams where you have collisions between two moving particles is a way to get to really high energies. So it's what we call a collider instead of a particle beam just striking a target. And when you do that, then you look at all the particles that come out. So that's shown in this picture here. We're going to take protons and photons. You might take electrons, but in this case, protons. They collide together and make secondary particles. And then we're going to figure out somehow the Higgs from all the other things that can happen, where I showed you before that in the previous slides, that what can happen isn't just sloppy background that's there, it's physics. So if you understand the physics, you can extract things. So it's a little different than just going into a laboratory and making a device sensitive enough. And in this case, you can see differences that you have to use to tell the difference. So, okay, so we build this big experiment. Historically, this was going to be done in the US, and it was going to be done on what was called the Super Collider. This is a picture of what was going to be the Super Collider. This was the biggest accelerator ever conceived, much bigger than the proton synchrotron at CERN. I'll show you the difference in size in a minute. And it was called the Superconducting Super Collider, kind of silly name. But the superconducting is because you can make higher magnetic fields to bend around the circle if you make magnets that are cool to low temperature using special materials. I'm not going to go through that. I don't have time here, but that's where the word superconducting comes from. And the second super is just that it's bigger than we think. So it was called the SSC. It was to cost $10 billion and in the 1990s, so it would be 20 billion or something now. And it was to be about 20 TeV. And one of the big goals was to do what I'm just talking about, what I've just talked about, and what I'll talk about how it was done at CERN. It turns out that there would have been a big advantage in being at these higher energies, and the Higgs would have been much easier to see. And I won't show you that because it's a waste of time. But in the US, this project was killed by a newly elected Congress in 1993. So here's a picture of the difference between what we have and what that would be. That was about a quarter built already. So they spent $2 or $3 billion. Underground tunnels were pretty much completed. And then it got canceled and they had to pull it all out and fill it with dirt. And so this big circle here is the Super Collider. From its concept, a picture of where the buildings were going to be and what they called the campus. But this is how big it was. This big accelerator at CERN that we're going to talk about now is this circle here. And in the last lecture, you remember we talked about discovering the top core. I've drawn that circle on here. Here it is. And I showed you for electrons this big long machine at Stanford, which is the Stanford Linear Collider, and that's shown in its length here if you put them on top of each. So these three exist. This is the one we're talking about today. And this was about a third or quarter built before it was canceled. And we know a lot more about particle physics today if that would have been completed, but it wasn't. So fortunately, this one was big enough, was first a machine for electrons. We're talking today about protons, but the ring was big enough so that if they converted it to protons and made it a collider, it was high enough in energy, although it was a harder task, to produce this Higgs particle. So it became a big goal for CERN to be able to detect the Higgs particle. The ring itself at CERN is 27 kilometers around, and it's essentially full from end to end with superconducting magnets. What do those magnets do? What are they there for? They're just there to bend the protons around a circle. Otherwise, they keep going. And so the superconducting magnets have more field than you can have in ordinary magnets, so you may, even though they're more complicated, they have to be run at low temperature. Basically the size of the ring, or conversely, the ring already existed. The energy that you can get to is determined by the size of the ring, because the magnets can only bend so much, and if you put more energetic particles in, they would be stiffer. Left with the problem to now do the Higgs on this machine, which is very impressive in its own right at CERN, the experiment was much, much harder. And when I show you the evidence for the data, it's quite an accomplishment, as you'll see, in being able to actually see definitively that you've detected this particle. The Large Hadron Collider itself at CERN costs about $10 billion over 20 years. And there's two experiments. There's about 3,000 scientists that work on what I'll show you is the data. So that's the size teams that it took to do this. The names of the experiments are just made by experimentalists. The one on the left, called Atlas, is just obviously named after a historical figure of sorts. And CMS is just an acronym for a compact muon solenoid. It describes the technical features of the experiment itself. This is a picture of where it is at CERN. This is the lake in Geneva. And you can see there's a big circle. It's actually underground. And it goes in the main laboratory is in Switzerland, but more than half of the ring is actually underground in France. That's actually not an accident. It's because the obstacles that keep you from digging a tunnel and safety requirements and all these things are much stricter in Switzerland than they are in France, so they put as much of it as they could in France. That's an aerial view, and now we'll kind of zero in on it and talk about it. So this is the ring. The actual place where the experiments are is about 300 meters, 3 football fields underground. Shafts that go down about 300 meters, and they're underground. You might ask why underground? I think it's less expensive and better to go underground when you have high radiation areas than to try to shield on the surface. So basically, large accelerators went underground where you can naturally use the ground for a shield. And here that works fine. In some places, if you try to put it underground, there's a lot of water underground. People like to drink water, so we have to be careful about radiating water. It's not a problem in this case, but it's practical issues. The two big experiments that I'll talk about are kind of on opposite sides of the machine. And then there's some other experiments that are done that I won't talk about. So there's a big, extensive research program done at CERN, but this is the overall concept. This is more of a view of then what's there. So if you go around this ring, which is 27 kilometers around, there's different installations where on the surface there's a whole bunch of buildings, electronics, all kinds of ways of dropping, and then they basically drop down a shaft, people down an elevator, and they have the apparatus downstairs itself. Maybe some of you have actually seen CERN, but probably most of you haven't. Okay, once you get down there, then the first element that's there is that you need these magnets that are going to bend the beam around the circle. And these are, as I said, superconducting magnets. And superconducting magnets are best ones that we know how to make today. They use niobium tin as the superconducting wire, and they're able to get 8 Tesla, that's the unit we use, which is about 5 times what you can do in a conventional magnet. So that enables you to go to high energy. When we say superconducting and we cool it, we actually cool it to about 2 degrees Kelvin. That's 2 degrees above absolute zero. And there's a lot of these magnets, 9,300 magnets. 9,300 magnets around. There's a reliability problem that you have to worry about as well. And they ran in, when they completed the machine in 2008, they found that only about tens of places, but 10s out of 9,300 sounds pretty good, they had a problem of shorting at the ends of these magnets where they connect them together, and they lost 1 year fixing that because they fixed then everything so that the reliability was even more. There's another kind of magnet. So there's the bending magnets, but there's also something here that says quadrupoles. And that's how you keep the beam focused. So the beam's going around this, but in time, by just hitting molecules and so forth, it'll diverge a little bit and grow. So you have to keep it focused somehow. That focusing is done with what's called quadrupoles. And then there are other specialty magnets and so forth. So basically, the only other number that's interesting is that the amount of power it takes to run CERN is about the same as what it takes to run a medium-sized city. It is 120 megawatts of power that comes in and runs this accelerator. Rome probably uses more than that, but a medium-sized city is about 100 megawatts of power. This is now the topology kind of starting from a proton and getting to the 7 trillion electron volts that they are going to be when they're colliding with each other at CERN. So they start, and it's also the history of CERN, because they built larger and larger accelerators since the 1950s when the lab was born. But they didn't throw away the old ones. They usually use them as the input into the next one. And you can kind of trace the history of CERN starting back in the lower energies here, the proton synchrotron, which is built in the 1950s, actually, and move on to the bigger ones and bigger ones. This is finally the machine they had for years. And I've indicated here how fast the protons are going by the time they collide. Biggest one is, of course, the Large Hadron Collider, and in this case, when they're going at 0.9999999, the speed of light, and then you're crashing them together. Total amount of energy, because they're going that far, is big enough to produce these Higgs particles. So that's the whole game. This is an actual picture of those superconducting magnets. They started this machine by running it at half energy, at 3.5 trillion electron volts each, and that wasn't enough to see the Higgs. So in the second step, they went up to the maximum that they're able to have at that machine unless they changed all these magnets, which is a proposal of some scientists, is to actually change to a more modern magnet 20 years later that could have twice the yield of these. That's rather expensive, replacing everything here. Instead, the general plan is to keep increasing the number of particles that are colliding, and there's a plan to do that, and they're doing that now. So the first goal is the one that I said, try to pursue this question of the Higgs particle, which is the origin of mass in nature, a pretty fundamental problem. But there's a lot of other problems that will keep the laboratory busy for a long time. Try to directly produce what might be the dark matter. When I talk about supersymmetry, you'll see that that's maybe a candidate for that. Understanding space-time itself, matter versus antimatter, a question I keep bringing up that we don't understand why everything's made out of matter in our universe. When we change energy to matter, we make as much antimatter as matter. and so forth. So this is just a graph of the history of them delivering particles, colliding particles at 99.9999991, the speed of light, over a period of a few years to collect enough data to show you the graphs that I'll show you. And when I show you the graphs, you'll realize that you need to run for a long time and have a lot of data in order to make a convincing case that you've seen this particle. So that means that there's a huge amount of data. And just to give you an indication, because some of you may like data computing and data analysis, it's about 15 million gigabytes of data each year that's produced at the CERN collider. That data is distributed around the world in what's called a grid computing system, which is very advanced, in a way that enables people, no matter where they are, you can be in Rome, and you submit your job to analyze the data. It may go onto a computer that's in the US, or it may go onto a computer that's in Japan. This grid works together, and where there's free time, job goes. So it's a kind of world connection. This is data. Not really, it's simulated data. So this is doing what I showed you in the very beginning, that is taking the best way we can calculate and then just taking a program and acting like it's the machine and the detectors and predicting what the distributions will look like that you detect. So on the left, proton making a Higgs and going to 2 gamma. What should it look like? Picking some mass for it. And remember these a little bit when I show you the real data. And so in this case, there's an irreducible background. This is that's going down, and a little peak that is, if you can reconstruct the mass, that's at the mass of the Higgs boson. Notice that this is a suppressed zero. Zero is really down here somewhere. So this is actually a small little peak. The second is different reaction if it was a different mass. So it's just a different simulation if it was in these masses, and you detect it in the final state of mu mu, what it might look like if it was 150 GeV, which is shown there. And you see that there's a peak that you can find, but you have to statistically determine whether it's significant compared to all that background. And then on the right-hand side is what if the Higgs boson were much heavier? We didn't know. And how would it be found? And so they looked at different ways to do that. This is then typical of what experimentalists do to try to not find out the problems when they're running or whether you're sensitive enough, but try to make a computer simulation that's realistic enough of a complicated apparatus or measurement so that you can actually find out or determine in advance how well you have to be and match your instrument to that. So the detectors themselves, I'll just quickly show you. There's 2. You might ask why 2, and that is, I think, in the simplest answer is that we believe a science result much more if there's confirmation. So in general, if you start and you only have one way to measure something, you may get false results that you don't believe. So from the beginning, they determined to have 2 experiments and make the 2 as different as possible, even though they look the same in this picture, as different as possible from each other in terms of its technical features and maybe the most sensitive features that you worry about in terms of doing the measurement. So that's why there's 2. There's a lot of information on here I don't have time to tell you except maybe the scale. The experiment on the bottom right is actually the CMS. CMS stands for compact muon experiment. And compact should mean small. It's not small. It weighs 14,000 tons, so it's huge. I'll show you pictures of it in a minute. It's about 30 meters long, and there's a lot of details which I can't go through here, But instead, I'll show you schematically what those details imply. There, it's essentially packed with the most sophisticated detection to do what needs to be done as you go out in size, both radially and in length. This is what it looks like. You'll notice there's probably people somewhere as small objects down near the bottom. Big things are these huge detectors with incredibly small, accurate detectors and electronics buried in the detectors. This is a picture again. You can see that people are pretty small compared to this very, very sensitive instrument. So when you ask why it took so many people, why there's so many scientists, there's all these specialized instruments put together to make these huge detectors. This is it a little more schematically for this CMS. The different parts of it, which have different labels on here, are typically made by different experimental groups. So the group that works on this, that's here at Sapienza, may have been responsible for a particular piece, and they do all the design, the instrumentation, and take responsibility for that piece. Of course, somebody or some group of people have to understand the whole picture well enough to actually use it, make it work together. Like a car or something, you have all the pieces, the carburetor, or spark plugs, or something else, and each one requires a specialized manufacturer and so forth, but it all has to come together to make it a car. And this is, in a much harder way, has a lot of very specialized instruments that have to work together. So this is the picture to kind of show you conceptually what happens. So this is just a slice of the detector. Looking at it, it continues to go around the circle, and the interaction takes place in the center. So the beam, there's a beam going at us and into the board, and they collide right at this point here. And then particles come out when they collide by the fact that when they collide, you've made an annihilation, and the secondary particles come out. At the beginning, the instruments are trackers that measure the momentum in a magnetic field. So the particles bend, and you measure their momentum. A lot of what's done after that are labeled as calorimeters. Calorimeters are a nickname for measuring basically the temperature. That's what you use a calorimeter for. Or in this case, it can be used to determine what kind of particle there is. So the first one here, just to say conceptually, is particles come out through very little material here. They enter this. It's typically, I don't know what this is, but it's typically something like lead sheets. And in the lead, the electrons will interact, make photons, they make more electrons, and it makes a little picture like this shower, and you measure that energy. And it's hard for it to penetrate further. That identified this particular track as an electron. Then you come out to the next one, there are particles that didn't do that. They went right through the lead, but they interacted later. They may be pi mesons or something. So basically the ones that go all the way through are particles that don't interact strongly. Those are the ones, remember, on the bottom of my chart, like called muons, and they would be on the bottom of this. So you divide up what kinds of particles there are, and then by how much they bend and so forth, what the momentums are, and measure the angles, and then you can reconstruct what I showed in those diagrams. So the idea is to look at something like 4 muons coming out, like shown here. They came about by making a Higgs particle that decayed into 2 Z particles that I only showed you about last week, and they decay into a mu plus and a mu minus. And that's the idea. And this is just some pictures that I won't explain to give you some feeling what the topology looks like for the experimenter that takes this data and then draws a picture of it on the computer screen. So this is an interaction, typical interaction of the particles coming in and going all over. They bend, the lines bend because they're in magnetic fields. Some of them go further than others because they're particles that don't interact as strongly, and so forth. And then the problem is to reconstruct all this and determine what actually happens. This is just a photograph of the tunnel and the superconducting magnets and another interaction. So that's what they look like. Now let me show you a little bit of data. So this is the result. This is after something like 5 years of running at CERN and claiming a discovery of the Higgs boson. So this is 2012, the time when the discovery was claimed. If you start on the left-hand side, you'll see a picture that looks something like one that I showed you in the simulation. And if we look at it here, that little bump is the evidence for the Higgs boson. That little bump is statistically significant when we look at it. So if we take and subtract what we know about this from this, we end up with this picture here. I'll show you this more, but you'll notice then that the signal is a really small signal compared to the background. Yet, this was an absolutely convincing discovery because all that I showed you before that seemed kind of complicated, understanding all the backgrounds, what they're really like, are really very, very well understood. So we know the shape of this background, which is physics, underneath it, and this little peak is the Higgs boson blown up here a little bit, and then in different decay modes. So that's the evidence that there's a Higgs boson. Believe it or not, with that little peak, people that understand the science sitting in, it turns out, in Melbourne, Australia, where I happen to have been at that moment, cheered, and in CERN auditorium when it was announced that they saw the Higgs boson in 2012. And this is a better picture of that blown up now, but you can see that the signal itself is about here. The actual mass we couldn't predict in advance, but now we know that the mass is about 125 B. That has implications in what this physics is of the Higgs, which we'll come to next. This is then a picture of how significant the signal was. So when we look statistically, we don't just look until we kind of are convinced by our eyes, but what's the probability that you get a shape like that on data statistically? And this is the buildup of that signal in probability, where you can see it's 10 to the minus 5 is the number right over here. When it gets below something like 1 part in 10 to the 5th probable that it's wrong, that it would happen statistically, then we decide it's either right or there's something that's fooling us, that it isn't a statistical problem. So in this case, enough had been done over enough time, so the scientific community believed that there was nothing that wasn't being taken into account that would give such a bump, and so you only had to look and see if the bump was truly significant at a level that you can claim that you really discovered something statistically, and this is the evidence that was used for that. Then they combined the two. I have graphs of showing that put together, measured how wide it is, has implications, and how it worked in different decay modes. The next question, and I'll go a couple of minutes more and then we'll take a break. The next question is, okay, so we saw this little bump, presumably this particle we've been looking for 60 years. What is its properties? And are the properties what we expected theoretically? Or are they different? There's things that are unique about this particle, which I'll show you. So first, quantum mechanically, some of you know quantum mechanics, some don't, but quantum mechanically, the particle is unique in that it has what we call spin zero, no spin. Different than other particles. We don't have another particle that's spin zero. This one has to be spin zero. I didn't show you any evidence, but that's the next question. If we really found the Higgs, then we can ask some questions about what its features are I'll show you the simple one that's easiest to understand in just a minute, but one of the other ones, for example, is the spin. Is there just a single Higgs particle? Turns out that since 1964, when these first papers are written, you can imagine imaginative theoretical physicists invented models that would have the Higgs boson, but maybe more complex cases, more than one Higgs boson, a family like we have in other particles. So is it single? Does it have zero intrinsic spin or angular momentum? That's what I just said. Another quantum mechanical property is, does it have even parity? This is a question we can ask tonight. Is it a neutral particle or does it have charge? It should be neutral. Does it interact with fermions in the way that we predict? And that's the part I'll show you. And it's impressively, in my mind, a way to demonstrate that this is different than all other particles and couples to mass differently than other particles. Does it interact with the other heavy particles that we know about, the W and the Z that we talked about last time, in the way that we think it would? So there's many, many physics things now you can try to do with the Higgs, and they're difficult because there's so much background. Remember, this is just a little peek over background. So it's difficult to do them. I'm not going to go through it at all in detail, but I want to show you, this is the different, answering those different things, but I'll just show you one graph because it is the most significant demonstration that we have discovered a particle that's different from all others and it's coupled in a different way to mass. So all particles that we talked about before and everything we talked about, if you remember the big chart that I have, has different interactions. We have a strong interaction, weak interaction, electromagnetic interaction, and gravity. 4 different interactions. They have different strengths. If we take what happens when you collide the particles together, we draw something like these Feynman diagrams, and the strength at one of those little vertices depends on whether it's a strong interaction, weak interaction, and so forth. But it doesn't matter whether I have, say, an electron going by and I have that interaction or a muon. It's the strength, which I've shown you in the last lectures, of the electromagnetic, strong, or weak interaction. It doesn't matter who's interacting, that's the strength. This one's different. It's supposed to have something to do with mass. So the strength of the interaction, instead of being strong, electric, or weak, depends on the mass of the 2 particles that are interacting with each other, instead of the just whether it's electric or magnetic or gravity or what it is. And this graph experimentally demonstrates that. What's shown is what the strength of the coupling, how often it happens that when you collide these particles together, you make the charm particle, charm quark, the tau lepton, the B quark, and what's shown here on this side is the masses of these different particles. So depending on when I go back and I showed you the data in the different ways, if it involved the charm particle or if it involved the B or whatever, if it involves the W and Z, which you remember were very heavy, then it's out here by 100 GeV. So each of these on this scale is whatever the mass of the particle is. What was seen, if I showed you the data in detail, is that the reaction strength grows, since it's a log-log plot, linearly with the mass of the particles. So that's the only case of where we collide particles together where the strength of what happens depends on how heavy the particles are. Just exactly what we want to be true if it's responsible for mass. So that's the convincing case. The yellow that I show, or the shaded part, is now more detailed theoretical ideas of some variants on the simplest picture of this model that Higgs people have. Maybe nature's a little bit different from that. They would all fall within this band. And so the idea is to try to measure things well enough to tell the difference between the different models that people have. So the standard model is this blue line. The range of predictions is the yellow band, where it might fall depending on what you measure, and the error bars are more or less what we're able to do. And I think I'll end here for before we take a break. So we'll take a break, and then I'll talk about this most popular model, supersymmetry, which we can't seem to find. And so 15 minutes and we'll start on that.